Okay, so this is number 15 from the Chapter 3 practice test. And this ends up being, this isn't an exponential growth, well, actually it is kind of an exponential decay problem, but you're using this formula called Newton's law of cooling, or it can also be thought of as Newton's law of warming. I've given the formula here and defined what each of the variables are. So T is the temperature of an object at time lowercase t. T sub s is the temperature of the surrounding medium. T sub 0 is the temperature of the object at t equals to 0, or whatever you treat as t equals to 0. And t, lowercase t, is time. K is a constant. So now let's go through the given information and see what we're solving for. So at 4 a.m., a body is found in a park. The police measure the body's temperature to be 90 degrees. So I'm going to write down that piece of information. So 4 a.m., the body is 90 degrees Fahrenheit. At 5 a.m., the medical examiner arrives and determines the temperature to be 86 degrees Fahrenheit. So an hour later, the body's temperature is 86 degrees Fahrenheit. So the body's cooling off, right? Which makes sense. Now, one piece of information that I did not include in this problem, and I'm finding is apparently not common knowledge, at least amongst teenagers, is that the average body temperature of somebody that is alive and does not have a temperature is 98.6 degrees Fahrenheit. So, assuming the temperature of the park was a constant 60 degrees Fahrenheit, that refers to the surrounding temperature. How long has the victim been dead? So basically, how long since the person's body temperature was 98.6 degrees Fahrenheit? Because that would be when they were alive. We don't know at what time that last was true. Before we can solve for how long the body has been dead, we need to figure out what K is, this constant K, for this particular, in this formula for this particular situation. So in order to solve for K, we need to be able to plug something in to all of the other variables. To do that, initially, you might think, oh, well, when the person's alive, that would obviously be T equals to 0. So you would plug 98.6 degrees Fahrenheit into T sub 0. The thing is, that's not super helpful because then you're not sure what, you can't use the other information as a data point, right? Like you don't know how long after the person died 4 a.m. is or 5 a.m. is. So what we can do instead is treat 4 a.m. as T equals to 0. So that then 5 a.m. would be T equals to 1. So 4 a.m. would be T equals to 0. That means 90 degrees would be T sub 0. And then we could plug in 1 for lowercase t and 86 degrees Fahrenheit for capital T. So filling in the formula now so that we can have our equation set up in order to solve for K, that constant K. We'll actually be able to solve for what negative K is, so we can just replace negative K. So we're treating T sub 0 as 90. Okay, so I plugged 1 in for lowercase t because if I'm treating 4 a.m. as T equals to 0, that means 5 a.m. would be, an hour later, would be T equals to 1. All right, let's simplify this equation. And if I subtract by 60 on each side of the equation, I would have 26 equals to 30 e to the negative k, and then dividing by 30, that's 13 over 15 equals e to the negative k. So now I can rewrite in the equivalent logarithmic form this statement. So negative k equals to ln of 13 over 15. And remember, you can always check that you've written that correctly by doing your arrows. E to the negative k would be equal to 13 over 15. So that is the value that we're looking for, right? That's negative k. So we have the formula T equals T sub S, right? T surrounding is still 60. Common mistake is to then, when you go to solve for how long the body's been dead, or you use the formula again, is to replace it with 98.6. But don't do that. The value we found for K is treating 4 a.m. as T equals to 0. So you need to continue to do that. I'm replacing negative K with ln 13/15 T. So we want to know how long the body's been dead. So we want to know how long since the body was 98.6 degrees Fahrenheit. So now I can replace T with 98.6 and solve for T. Okay, so subtracting by 60, that'd be 38.6. If we divide by 30, equals e to the ln of 13/15 times t. Okay, so now we're ready. We have e by itself on one side of the equation. Let's rewrite this in its equivalent logarithmic form, which would be ln of 13/15 times t equals to ln of 38.6 divided by 30. And remember, you can always check, draw your arrows. So e to this power equals to 38.6 over 30, and that's true. So then to finish solving for t, just divide by ln of 13/15 on both sides. So t, the exact value of t would be ln of 38.6 over 30 divided by ln of 13 over 15. This represents the exact value of t, which we would predict to be, or we know that t is going to be a negative value because we're treating t equals 4 a.m. as t equals to 0. And you know that the body was alive before 4 a.m., right? Since at 4 a.m. and then 5 a.m. the body's temperature keeps decreasing as it's been dead for longer. This makes it difficult. Leaving as the exact value makes it difficult to describe or write a summary for how long the victim has been dead. So let's look at what the approximation is by typing that into our calculator. So I'm typing in ln of 38.6 divided by 30 divided by ln 13 over 15, and I get approximately negative 1.761. So that means at 4 a.m., as of 4 a.m., the victim would have been dead for approximately 1.761 hours. And if you wanted to write your answer in relation to 5 a.m., you could say at 5 a.m., just add on an hour. So approximately 2.761 hours.